Welcome back to Calculus 2, Section 2.7, Integrals, Exponential Functions, and Logarithms. We have a few different things to go over. We're going to start with the natural logarithm as an integral. All right, to get started, let's recall the power rule for integrals. If you think about differentiating a polynomial, then we can rephrase that as an integral. If we have x raised to a power, we know that we increment the power and then divide through that by that power. As an indefinite integral, we always pick up a constant of integration. Looking at the value that we're dividing by, we never want to divide by 0, so this formula holds for every value except for n equaling -1. And then that opens up an opportunity to make a definition for the natural log to see how we might be motivated by that. Let's think about the fundamental theorem of calculus. If we take the reciprocal function 1 over t, and we integrate from 1 up to x, we throw a derivative on this. The fundamental theorem of calculus tells us we will get 1 over x, and thus that verifies that this function here is an antiderivative for 1 over x. Here's a nice little video. We have a blue shaded region, then it turns to red, blue for positive, red for negative. We have a black dot that's changing its location. Currently the black dot is bigger than 1, getting a blue shaded area. The black dot is now less than 1, getting a red negative shaded area. And then you look at where did the shaded region change from blue to red at the x value of 1. So we're looking at a shaded region from 1 to x, and then the curve is the reciprocal curve, 1 over x. And this is our definition of the function ln of x, which goes by the name natural logarithm. And thinking of the video we just watched, 1 up to x is the bound of integration. Under what curve? The area under the curve, the reciprocal function, so integrand 1 over t. All right, so this is the definition of the natural log. Now let's look at some properties of the natural log. And there will be quite a few. Here is the very first one. We've kind of already done this. We recalled the fundamental theorem of calculus. The natural log is an integral with integrand, the reciprocal function. So if we differentiate that, we're going to get the integrand. That's the first property, and let's employ that first property. Here we're taking our function f to be given as a composition. The outer function is the function that we just defined, but then it's a composition with some inner function. We need to use the chain rule. So taking a derivative of this function, the outer function is the natural log. Its derivative is 1 over input. The input here is this polynomial quadratic. And then the chain rule, we differentiate the input. This polynomial has a straightforward derivative. Go ahead and compute that. 2 comes down, multiplies with 3 to get 6. And we have our f prime. Nice. Do another example. Let's make the function f a little bit more involved. Again, this is a composition. We are squaring a natural log. That's the outer function. So if we want to compute the derivative of this f, we're going to bring that power 2 down, decrement the power to a power 1, and then evaluate at the inner function. But this inner function is going to be differentiated, but note it's also itself a composition, so we'll apply the chain rule one more time. So we have 2 times the natural log, we copy that over. Taking this derivative, that's again a chain rule computation. 1 over input, the input is 3x. And then differentiate that input. The derivative of 3x is going to give you 3, yielding a cancellation, so we simply have to move the 1 over x out into the front. Excellent. That was property 1. The derivative of ln is 1 over input. Property 2. The natural log is continuous. Well, the natural log has a derivative, and differential functions are continuous. So the natural log is continuous. Moving on, property 3. Property 3, let's watch a video again. You might recall that the red graph is the graph of the natural log. And then if you take the red graph and you reflect it in the y-axis, you get the blue graph. The green graph is giving you the tangent line at any point. And then currently we're looking at the tangent line to the blue graph at about x equals -2. Think if you were to reflect the black dot across the y-axis and produce a point somewhere over here, can you imagine the tangent line is going to be a reflection of the green line? Then this green line currently has a negative slope, but if you were to reflect it across, it would have a positive slope. But the amount of rise and run, ignoring the pluses and minuses, would be the same. And then taking the red graph and the blue graph together is the graph of the natural log of the absolute value of x. And then the derivative, since the slopes of the green tangent line would be the same whether you're on the red graph or the blue graph, then the derivative of the natural log of the absolute value of x is 1 over x. Now, note that this is holding for x not 0, so x can be positive or negative. The natural log must take positive inputs, thus we need the absolutes on the x. But over here on the right-hand side, if we were to plug in, for example, that -2, then the slope of the line tangent should be negative valued, and indeed you'd get 1 over -2. Okay, and this property 4, is actually rather important. You want to put a star next to that. We're using it here in property 4, that if we take an indefinite integral with integrand, the reciprocal function, then this is not placing any restriction on the inputs x. That this property 4 is saying that you can have inputs negative x's. And to accommodate that, we're going to write down the most general form, would be the natural log of the absolute value of x plus a constant of integration. All right, so this is a very important property, these two. Nice. Let's go ahead and do an example of that. Okay, take a look. You've got both sine and cosine appearing. Let's pick the bottom one, sine. In a u substitution, we want to evaluate the indefinite integral. Do a u substitution. Sine differentiates to cosine, therefore we have our differential du. We can swap out. Cosine dx appears as a numerator, thus becoming new differential du. And the sine of x appears in the bottom, thus we get a u as a denominator. And voila, this is exactly the form of the property that we just studied. This will be the natural log of the absolute value of u plus a constant. Then to finish things off, we started in the variable x, so we return to the variable x, and we're done. And again, note very carefully the absolute values. Beautiful. Your turn. Think about the example that we just did. Integrand cosine of x over sine of x, whereas tangent as a quotient identity is the reciprocal of that, sine of x over cosine of x. So it's the same problem, except that you're going to have to deal with a minus sign. Property 5. This is on the natural log. And property 5 is this theorem stated out in 3 different statements. We're going to look at the first 2, and the third one will be an assignment for you to show. Okay, statement 1. The natural log of 1 is 0. Well, we go to the definition of the natural log. It was definite integral from 1 up to input, but here the input is 1. So having a lower bound and upper bound of 1 leaves you no area to carve out. So that's the first one done. Let's move on to the second one. And to show the second one, we're going to use this property of integrals. Remember, the natural log is given in terms of an integral. Bounds of integration a to b. That we can interject a c and come up with a sum of definite integrals, provided that each integral, the 2 on the right, makes sense. All right, so we want to use that. So let's start this property 2, the natural log of this product AB. Well, that's a natural log of this input must be the integral from 1 up to that input of the reciprocal function. Good, that's just a definition of the natural log. And then let's use this property up here. Let's interject a. So take it as an upper bound, then take a as the lower bound, and then finish up at a product b. And then note that this first integral is matching the natural log of a. So we're going to spend our time on the second integral. Let's go ahead and copy where we were. Natural log of a product b interjects an bound of a as an upper and lower, and concentrate on this second integral. So in the second integral, let's make a u substitution. Let's do the bounds first. If we have a lower bound of a for t, then we're going to have a new lower bound of 1 versus an old upper bound a product b plugged in for t. A's will cancel out, and we'll get a new upper bound of b. All right, that's good. Let's go ahead and then also consider what's going to happen with the differential. du, well, t is the variable, a is a constant, so the right-hand side will simply be dt over a. Note that if we want to swap out for t, that t is a times u, and thus we're going to be able to achieve an a in the denominator. And so we're going to come up with the second integral with this substitution, takes our good form. It is exactly the natural log of b. Recall that u is a dummy variable just as t is a dummy variable. These are definite integrals, so we have natural log of b plus the natural log of a, establishing that second part. Here's an assignment for you. A lot of different hints here. Let's look at what you're to establish, that the natural log of x to the r is r times the natural log of x. This is a property of logs that you would have studied in an algebra class. Now, you can open up the book and follow along in the book, and you can follow these hints to do this proof. Differentiate the left. This is a composition of the natural log with a polynomial. We know how to take its derivative. Second, grab the right-hand side and differentiate it. Keep in mind that the r is a constant. So this right-hand side under derivative will be nicely r over x. Then show that these two functions, the left and the right, have the same derivative. All right. Then 4, use the fundamental theorem of calculus to conclude that the two functions must differ by a constant, so that these functions are both antiderivatives of the same function. And then show that the constant c must be 0. Okay. Excellent. Another assignment. As mentioned before, we've done statement 1, we've done statement 2. Now you can rely on statement 2 and use it to prove statement 3. Or you can work statement 3 as we worked statement 2. Either way. That was the natural log. We're going to move on and come up with the natural exponential. But first, we need the good base e. And here we have a definition that this number, real number e, is the number such that when you give it to the natural log returns 1. Let's come back to our picture definition for the natural log. That it's the integral from 1 up to x of the area carved out by the reciprocal function. We're looking at a picture. We're looking at an area of exactly 1, and then that's going to correspond with the input e given to the natural log. And then you want to make a note that e is a value that sits between 2 and 3, but closer to 3, 2.7 something. All right, so that's a definition of e, and we want to use that to generate the inverse of the natural log. To show that we're on good footing, let's go back and think of one-to-one functions. Every output has exactly one input. That's a one-to-one function. And why do we care so much about one-to-one functions? Well, if you have a one-to-one function, then you can rely on that one-to-one function being invertible. And for that, we can think graphically. Blue curve here is defined for x is positive. The blue graph is only sketched in the right half plane, takes only inputs x positive, but outputs are all y values, so the output is the entire real number line. To invert this graph, which is a one-to-one function, think about horizontal lines will only intersect the graph in one location. To invert the graph, we first plot out the line, the green graph, y equal x, and then reflect across that line. Take note that the blue graph tends towards the y negative axis, so that when we reflect that, we're going to produce a graph which will tend towards the x negative axis. So the blue graph is asymptotic with y negative, and this reflected red graph is asymptotic with x negative. The blue graph intersects the x-axis at x equals 1. The red graph intersects the y-axis at y equals 1. Nice. What can we label the curves? Y equal ln of x. Simply interchange, since we're changing between y's and x's, we're interchanging x equals ln of y. Y equals ln of x. Well, we're actually going to prefer to look at the red graph as the graph of a function of x. So we'll adopt the notation e to the x. As the red graph is the reflection in the line y equal x, the red graph is the graph of the inverse function to the natural log. So we've already introduced the natural logs. We're now introducing exponential functions. We've done properties of the natural log. We'll do properties of the exponential function. Okay, a little bit of notation. E to the x, we can equally write down as exp. of x. E to the x is the same thing as exp of x. Okay. Now, this e to the x, or exp of x, is the inverse to the natural log. This is the natural exponential. By being inverse functions to each other, that means their composition will yield the identity function. If we want to plug something into the natural log, that something must be a positive value. So the first statement is only holding for positive inputs. On the other hand, our reflected graph, the red graph that we had, was defined for all inputs so that the second statement holds for any input. Okay, note that the composition of one function with the other function is producing back the original input. This is the identity function. Okay, let's make the theorem here. 3 different properties. Let's take a look at the first one. That if we take a product of exponentials, that we get an exponential of a sum. Let's show that. So we're going to show this first one. And let's take this product of exponentials as our input to the natural log. And then apply that this is the natural log, use the property of logs, natural log of a product. This term times that term. So we get a sum of natural logs. That's a property of logs. Next, let's use that one-to-one property of the natural log and the exponential, that this essentially becomes the identity function. So it's going to return the input, p. As well, this is the composition of the function and its inverse, so it returns back just the input, q. Excellent. And then the left-hand side we're leaving alone. Do this once more. Well, we can look at it from another perspective. Let's treat this as the output. Well, then we could pass it in to the composition of ln and e. So if it's passed in as the input to ln and e, then as output, it will just be itself. Excellent. Well, we're actually done because we know that the natural log is a one-to-one function, meaning that if these outputs are agreeing, then it must be the case that the inputs on either side must also agree. That's what a one-to-one function does. And this last statement is exactly what we wanted to show. Beautiful. So then for your assignment, you get to finish establishing these 3 statements, 2 and 3. We've already done statement 1. Excellent. Another verification. You have the integral of e to the x dx. You want to verify that its antiderivative is the natural exponential plus any constant. And you want to think in terms of antiderivatives. And then to accomplish that, logarithmically differentiate y set equal to e to the x so that you can achieve that e to the x has derivative e to the x. Say that again. You want to observe that e to the x has derivative e to the x. And then appeal to the definition of an antiderivative. Very good. So we've done the natural log, we've done the natural exponential, and we've done properties for both functions. And up to this point, we have relied on a very particular base e, the natural base. But the exponential b to the x is a one-to-one function. So if you set up x equals b to the y, then you can write down y equals log base b of x, that these two things are inverse to each other. You can sketch that out. And then let's play around with this a little bit. Let's take this right-hand side, and let's do the natural log of this right-hand side. Natural log of x, natural log of b to the y. Okay. Then let's use a property of logs to bring that y out into the front. Clean up by removing the parentheses. They're not needed. Use a property of logs. Y is out in the front. And then solve for y. Solve for y. Okay. All very good. We took the natural log of this right-hand side, used the properties of logs, and isolated the y. So now we look at the other side, and we see that the y is actually a log of a generic base b of input. So we're finding that log of a generic input b can be expressed in this particular base e natural logarithm. This is called a change of base formula. All right, well, we're doing calculus. We would like to be able to differentiate this generic base b logarithmic function. Easy. Given our change of base formula, taking a derivative of this left-hand side, which we can also call y, dy dx, is taking a derivative of this right-hand side, but ln of b is a constant. And we know constants pull through the derivative, and we know how to differentiate the natural log of x. It goes to 1 over x. Beautiful. That's it. We're done. We now know how to differentiate any any logarithm of any base. It's 1 over input, but if the base is not e, then you have to tack on a 1 over the natural log of that base. So here it is written out again. This is what we just established. Good. Well, how about if you have any base, but any base for an exponential function? Okay. And then what's going to happen? Likewise, you're going to get back that function, but multiplied by the natural log of the base. Recall that if the base is e, then ln of e, what does that equal? Ln of e is 1. Right? All right, so how do you verify this? Here's the hint. First, make sure that you agree. If you're taking y to be b to the x, then y can also be written out as e raised to the x product ln of b. Right? So that property, logarithmic property, that x can come up, and then use a 1-to-1 property on e and ln. Okay. Then once you've done that, you then differentiate this expression and use the chain rule. Use the chain rule in this expression to verify the given expression. Excellent. And that finishes this video. Thanks so much for watching. See you on the next one.